First of all, I'd like to thank all the people that have tuned in today, and I'm happy to teach you how to simulate chemistry on a quantum computer. This is going to be the first part of a two-day lecture. So I think tomorrow there's going to be the second part. And without further ado, let's start to list the topics that I'm going to cover in this class. But first of all, you're going to learn how to construct qubit Hamiltonians for molecules. And then, so this is going to entail learning something about second quantization notation for fermionic system, which is what we use really to map molecules to map molecules to qubit objects. Then I'm gonna introduce you to some basics of fermion to qubit mappings, and then finally I'm gonna teach you why variational quantum algorithms work, why they work on the current noisy devices that we have, and what are some popular variational wave functions for VQE, for variational quantum algorithms, and finally a bit of open challenges. And I hope at the end of this class, you should be able to tackle the lithium hydride challenge as Brian was mentioning in the introduction. Okay, the first subject of this class is how to build qubit Hamiltonian out of molecules. But first of all, let's explain how to get molecular Hamiltonian first in fermionic second quantization language and what that even means. Actually, before diving into molecular and fermionic Hamiltonians, just a few words on why we're interested in simulating quantum chemistry on quantum computers. Well, the thing is, quantum chemistry, it's a really nice application because it really sits here at the intersection of these three interesting features. So it's a problem for which we certainly have a quantum speed up. It's a problem that doesn't require many qubits as other ones, for example, condensed matter or high energy physics problems, and also has some practical applications. So you can think of actually really addressing a state-of-the-art real-world problem with some hundreds of perfect qubits. Okay, so noiseless qubits, which is not what we have now, but still the amount of hardware that we need to tackle chemistry problems, it's way less. Okay, so that's why we are focusing so much on quantum chemistry, and that's why also this class is about solving quantum chemistry with quantum computers. Okay, now the question is, what can really quantum computers do for quantum chemistry problems? Well, they can certainly target ground state properties, so we'll see what that means. But for the moment, you can, what I'm going to tell you is that the access to ground state properties for molecular systems gives us access to useful information, such as reaction rates and molecular structure. Okay, so we'll see what that means in a few slides. Okay, this is a first quantized molecular Hamiltonian. So the ones of you who have a chemistry background will certainly recognize this Hamiltonian. This is basically a model for the interaction of a set of electrons and a set of nuclei. So you know a molecule is nothing else than a collection of atoms in space, which is somehow very stable energetically. Okay. So this is our molecule. You see it here. So if we draw a reference frame in a three-dimensional space, we see that this molecule, it's characterized by the coordinates of its atoms. So we have three atoms here, and their coordinates, for example, we can call them RA, Rb, Rc, and then we're going to have a bunch of electrons floating around quantum mechanically in orbitals around these atoms. Okay, and this operator here, the Hamiltonian, it really gives you the energy, the quantum mechanical energy of this system comprised of a bunch of nuclei and a bunch of electrons. So we have a term in this energy which describes the kinetic energy for these electrons, a nuclear kinetic energy, a electron nuclei Coulomb interaction, which is actually attractive because electrons are negatively charged while nuclei are positively charged. An electron-electron repulsive Coulomb interaction, and the nuclei again repulsive Coulomb interactions. So the name of the game here is we want to know what is the minimal eigenvalue of this operator. So what we are targeting is a time-independent Schrödinger equation. Which is this equation here. So what we really want to know is what states psi satisfy this equation, where h here is the operator defined. This h is the same operator defined up here. And specifically, we would like to know the ground state energy. So we would like to know for which value of E, which is the smallest value of E that satisfies this equation. And so you can see that in this Hamiltonian, we have the nuclei coordinates, this RAB, and some electron coordinates, this RIJ. So you can think of the Rij being the electron coordinates. Okay. Again, so this H is an operator acting on quantum states. So H can be represented as a matrix. And we are interested in knowing the lowest eigenvalue of H. So we want to know the value of H0. So we want really to know that the minimal, the smallest eigenvalue of this Hamiltonian H for which this equation is satisfied. Well, so why is that interesting? That's interesting because knowing the value of E0 for different spatial configuration of the atoms in this molecule will give us access to something like reaction rates for molecular reactions, and that could be that could allow for example, the discovery of new drugs or the design of new materials, if you want. So the way it works, it's this one. So imagine, again, I told you that a molecule is completely specified by the coordinates of its atoms. So imagine that we plot the energy of this molecule, which is really the average value of H over some quantum states, as a function of the coordinates So as a function of the coordinates of the atom that compose this molecule. And then we can explore, so we can search in this landscape here, and we can explore this landscape and check what is the value of E0. I guess I should write this 0. What is the value of E0 for each value of the spatial coordinates of the atoms that compose this molecule. And this is useful information because you can think of a reaction rate, so the speed at which a certain reaction occurs, as depending exponentially on energy differences in this landscape. Okay, so if we find E0 at this very high energetic point and E0 at this low energetic point, this energy difference delta E0 is going to give us information about the reaction rate that's happening in our lab, for example. Okay. And so this will allow you to make predictions of reaction rates without actually going to the lab and trying different, try a bunch of reactants and see what sticks together. And the good thing about this is that the good thing in using quantum computers to target this is that this problem is an exponentially hard problem. If you want to target it with classical methods, whereas with quantum computers, this has some exponential advantage, at least, let's say, at least from a memory perspective. Okay, so encoding, loading the ground state and trial states for this Hamiltonian cost function has a exponentially improved benefit with respect to targeting the same problem with classical computers. And we're going to solve this problem. We're going to tackle this problem in the Born-Oppenheimer approximation. So in the Born-Oppenheimer approximation, basically you can think of it as the nuclei of these atoms, like being fixed in space and not moving. Okay, so think of this problem. If you want to have a classical intuition about this problem, you can think of a bunch of really like a bunch of balls, like attracting and repulsing each other. And you can think of some of these balls being much, much heavier than the other ones. And so the heavy balls are the nuclei, which are thousands of times heavier than the electrons. And so, of course, an object which is thousands of times heavier than the other one, when they interact together, it's not going to move. Okay, so it's not going to feel too much the repulsion of between the two objects as the lighter one, the lighter object. Okay, so this is the spirit of the Born-Oppenheimer approximation. So the Born-Oppenheimer approximation tells us that the nuclei are fixed, and we're only dealing with a bunch of electrons quantumly, moving around these nuclei. And this is a lot of beautiful words, but mathematically, what this means is that we can neglect this term in this Hamiltonian, because remember that this was the kinetic energy of the nuclei, but since they're not moving, now this becomes zero. And also this term here, which was the Coulomb contribution to the molecular energy coming from the repulsion of these nuclei, which are now static, which are now fixed position in space, it becomes just an energy shift. So if you want, we have simplified the problem. So what we're really dealing with is a problem of interacting electrons. Which is still exponentially hard, but somehow better than the full region problem. Okay, now let's start to see like how these nuclei and electrons are even, how we can even hope to map them into a bunch of qubits. So in the state of qubits living in our quantum hardware, for example, in the IBM quantum processors. Okay. So I hope that from the previous classes you get some basic concepts of what is a wave function and what is the wave function or the state of a bunch of qubits. But now something that I would like to have you reflect on, and I'm sure I think nobody in the previous classes told you, is that qubits are distinguishable. Okay, what does this mean? This is very precise meaning. Okay, so if you take two qubits, for example, qubit 1 and qubit 2 in this nice picture of IBM superconducting processor, then their wave function can be this one. So this is qubit 1 and qubit 2. Okay, so qubit 1 is in the chi1 state, and qubit 2 is in the chi2 state. Okay, so this is a physical meaning. So it means that when I go to my device and I measure this guy, and I physically know that it is this qubit sitting on this specific position of the chip and so on, this will have the state chi1. Well, while this other guy will have the state chi2. Okay, so this seems like kind of like a trivial thing, but it's not if we start to talk about electrons. Oh, electrons are actually not distinguishable. Okay. Electrons, or if you want in general, fermions, they are indistinguishable particles. Or sometimes people call them identical. Okay, so this means that mathematically has a very precise meaning. So it means that the total wave function for a system of two electrons cannot be of the form that I showed you before. So it has to be this form. Okay, now look at this function here. So now we don't know anymore which one of the two electrons in this case is in the state chi1 or chi2. So this information is completely undetermined, right? It's undetermined because, this is an antisymmetric superposition of this state here. So the message that I'm trying to pass you is that electrons and fermions are always in a wave function state of this form. Okay, so you cannot tell in any situation if a certain electron is in a certain state. Okay, so that information is scrambled between all electrons. And note that this is a antisymmetric wave function. Okay, so antisymmetric means that if I exchange particle 1 with 2, it takes a minus sign. Okay, now you may be wondering, but why that is the case? Well, that's not really up to us to explain, at least maybe not at this level. There's something like more fundamental that you could say about this, but really what we are dealing with here is that this is how nature works. Okay, so this is really like a fundamental phenomenon, and so if you ask me why this is the case, I would say this is how nature works. Okay, so fermions are always in an antisymmetric state. Okay, so if we are convinced of this, I guess we have to be convinced of this fact. By the way, the antisymmetric nature of the fermions has a lot of implications in a lot of things. For example, thermodynamical properties, right? So the thermodynamics of fermions is very different from the one of distinguishable particles, but we're not going to cover that here. Okay, so for now, we're just going to assume that a generic fermionic wave function is antisymmetric. Okay, so this was an example for 2 qubits. Now, what if I have this wave function here? What's a 2-qubit example? What if I have n qubits? How do I write down a generic antisymmetric wave function for n fermions? Okay, so for n fermions, what we have is that their wave function can be written as a linear superposition of determinants. Okay, so now I have n fermionic states, which let's start calling them n fermionic orbitals. Okay, so I have chi1, chi2, up to chi-n fermionic orbitals, which means fermionic states, and these states are antisymmetrically distributed among n particles. Okay, so n electrons. At this notation here, it means that this function is a determinant. Okay, so these 2 lines that you see here, it means that we are taking a determinant of this matrix made up of wave functions. Okay, and this determinant here, it's called a Slater determinant. And you can express always any fermionic wave function of n electrons sitting in n atomic orbitals as a Slater determinant. But this notation, it's kind of like very tricky, as it's very involved, right? So this determinant has a lot of terms, and we don't really want to carry around each time like this very heavy notation. So let's define a more agile notation for this kind of antisymmetric wave function. Okay, so let me define this, the wave function of my system, in this way. So this is a anti-symmetrization operator. So it takes this state here, and it creates an antisymmetric superposition of this state and other states which have their orbitals swap between the different electrons, such that a permutation of any two electrons in this wave function is going to result in a total minus sign. Okay. But also, this can be defined in a more compact way. Okay. And the way it can be defined is that I'm gonna use bit strings to define the state of my fermions in my system, and I'm gonna place a 1 or a 0. Okay, so whether there is an electron or not in the ith orbital, in the ith fermionic orbital, or fermionic mode, if you want. So since in this case we have n electrons in n modes, we're going to have all ones here. Okay, so this state is exactly n electrons distributed on n modes. Okay, but other number of possibilities other possible configurations are allowed, right? So I can have, for example, m electrons distributed on n orbitals. Okay, so instead of having states of all ones here, I could have something like that. Okay, so this will be a state with n particles, n electrons, and this will be a state with of n minus. Okay, of less number of electrons, because some of these orbitals are not occupied. And so this way of representing Slater determinants, it's called a Fock space. So the Fock space of n orbitals, it's basically the collection of all these subspaces which have a fixed number of electrons, n less than big N. And it's technically the direct sum of all these subspaces. Okay. And practically what I'm trying to say is the space that we are considering, it's something like this. So it's a big matrix, and you have states with 0 particles. Let me say 0 electrons. And then we have subspaces with 1 electron. subspaces with 2 electrons and so on. 2 electrons. Okay, so this is the 0 electron subspace, 1 electron, 2 electrons, and so on, up to the subspace with n electrons. This one here. And so, of course, now you realize if I ask you the question, how many states are in the subspace of n electrons? Well, the answer is just 1, right? Because there's only one way of putting n electrons in n orbitals. And that's correspond to the bit strings filled with all ones. Okay. But that's the same for the subspace at 0 electrons as well, right? So there's only one state here. So the state with only zeros. But what happens in these subspaces? Okay, so there's more than one state, and actually you can show that each, if you want, small n particle subspace has a number of states which is n choose big N choose small n. And so, every one of these subspaces has this number of states, but all together, the number of states is 2 to the n. Okay, and so this fact that the number of states is 2 to the n, it makes something click in our head, right? Because also the number of states of n qubits is 2 to the n, right? So at this point we are starting to see how we could even think of a mapping between this the space and the Hilbert space of a bunch of qubits. Is there any question, Brian, so far? Maybe this could be a good time for questions.
Yeah, of course. I'm going to read you one question that's been submitted, and then I'm going to ask everyone in the chat. I see a few people have asked questions about this particular slide. So as we're answering the first question, if you want to write in the chat any questions about this particular slide, I'll read those back. But your first question, what is the current accuracy of the molecular interaction simulated by a classical computer, and how much can it be improved by using a quantum computer? I think you're pretty much a perfect person to answer this question.
Yes. So I guess if this question is coming from a chemist, then I can tell you that quantum computers tackle full CI precision. Okay, so in principle, the precision that we could get with a quantum computer is equivalent to the full exact diagonalization of the Hamiltonian that you're trying to tackle. So this, I think this should answer the question. Maybe there is another way of answering this question. Actually, with this matrix here, yes, maybe I can try to do that. What a lot of classical methods do, now that we have this matrix up here, let me actually change the color of my pen. Okay, so wait, what am I? I couldn't figure out a keyword for, sorry, a combination to change the color of the pen. So
no worries.
So a lot of classical methods, so what they do is they take these subspaces And they only diagonalize this problem in, so, you know, they take the one electron, or maybe sorry, it has to be fixed number. So they take the 2 electron subspace, this subspace, and they only consider a only some rows and column of this subspace. Okay, so they're not targeting the whole subspace. Okay. So what we have with a quantum computer is could be actually in some limit this whole matrix here. Okay. So this would be, this could be what a quantum computer could do. Okay, while your classical method is typically limited to some subspace. Okay, I think this should answer the question.
Yeah, I think so too. Thank you very much. And then a few questions just about this slide in general. We're looking for a few clarifications. The first question we have, about just a clarification, is, are we already using atomic units?
Oh, we can. I guess the question is also, there's 2 different way of interpreting this. Are they referring to atomic unit distance or atomic orbitals?
Well, that was another question, was actually about the orbitals. Someone asked,
Yes.
Is the column axis the number of orbitals?
So, okay, first question. It doesn't matter if we use atomic orbitals or molecular orbitals. It doesn't matter. We can feed both of the description for a molecular Hamiltonian to a quantum computer. So that doesn't really matter. And also the the units that we use to measure the interatomic distances also don't matter. Actually, you can change those. And what was the other question, Brian?
The other question was, is the column axis about the number of orbitals? On your, on the table you have set up, is the number of orbitals the y-axis?
No, it's the number of states that it's the number. No, it's not the number of orbitals. It's the number of states that so it's the number of ways in which you can put n electrons in n orbitals. So small n electrons in small n orbitals. So that's what the column are. Okay. Gotcha. So the size of this matrix is not n. The size of this matrix, as I said, is 2 to the n. Okay. So it's the number of states that you can have in your quantum system. So it's not just number of orbitals.
Perfect. All right. I think I'll give it back to you to continue the lecture. Thank you.
Okay, thank you. Yeah, those are very good questions, and I again encourage you to ask more. Okay, let me get back to my black pen here. All right, so now we talked a little bit about the Fock space. Now let's see how we can define operators on this Fock space. And specifically, I want to define creation, annihilation, operators on the Fock space. Okay, so the Fock space is this whole space that I told you before. And I want to define them with this. Let me just give the definition, and then I'll motivate why that's the case. So a creation operator on the ith orbital would act in this way . So it would act this way on a state with Ni fermions on the ith orbital. And similarly, we have an annihilation operator, which is going to have this action. This is J minus, I. This is I, right? This is not 1. So J less than I. So this is N plus 1. Okay, so let me comment a bit on this. So what's happening here is that, first of all, let's have a look at these prefactors here. Okay. By the way, this Ni, so the occupation of a certain fermionic orbitals can be either 0 or 1. Okay, so you cannot have two particles, so two electrons, sitting on the same orbital. And the reason that's the case is you got to think of our definition of a state in the Fock space, right? So a Slater determinant. So you know that a determinant is, so this determinant will be 0 whenever we have two orbitals which are the same, okay, which will mean two electrons in the same orbital. So these occupation numbers can be only 0 or 1. Excuse me one second. And so since they can be only 0 or 1, then the action of a creation operator can be only raising the number of orbitals that are in the, raising the number of particles by 1 unit, the number of particles sitting in the ith fermionic orbitals by 1 unit if there is no particle, if there was no particle before this operator was acting on this state, right? So if we had a 0 here, we would have a 1 on the other side. And if we add a 1 here, so if we add an electron already in that orbital, then this prefactor here would result in the annihilation of this Slater determinant. Okay, so there's a bunch of facts here. So that cannot be two fermions in two electrons in the same orbital. By the way, this is called also the Pauli exclusion principle. So the Pauli exclusion principle tells us that there cannot be two electrons on the same orbital, and the action of a creation and annihilation operator reflect this this fact. And so, of course, you realize also the annihilation operator as a similar action. If there is no electrons in the ith orbital, it's just gonna annihilate the state. And if there is one electron here, then it's gonna bring him down. So it's gonna remove the electron out of that orbital. More interesting are these phase factors here. So actually these phase factors are necessary to keep the anti-symmetrization properties for Slater determinants. So if I want to define a state for my fermions, for my electrons, which is a linear combination of different Slater determinants, and then I want to act with creation and annihilation operators on this linear combination, I need to take into account of these phases to keep the whole state antisymmetric. Okay, that's why those phases are there. And from this definition of these operators, sorry, I think I have a problem. 1 second with the video here.
We're able to see you and hear you clearly.
Yeah, it's just my monitor. Okay.
Oh, I see.
Maybe it's fixed. So from this definition, we can actually derive if you want. This is a little home assignment. I'm not going to do here. I'm not going to do it here because it takes a while, but we can derive the anti-commutation relations for the fermionic creation and annihilation operators. So I guess what I'm saying is this, that the anti-commutation, which is this this sum here, so it's a product of operators, and then that the same product is just exchange the positions, which we can write in a compact form like this. This is delta ij. Okay, so this means is 1 if I is equal to j, and it's 0 otherwise. And so we will see that this anti-commutation property of the creation and annihilation operator is very important, and it's going to be hard to mimic when we go into a qubit representation of these operators. And of course, you have other algebraic properties of these operators, like the commutator. These commutators are 0 and so on, but this is really the important property that we're going to have a hard time to retrieve when we go to qubits. Okay, so I gave you the definition of creation and annihilation operators. A-DAC I, and actually what I can tell you is that we can use them to build any operator acting on our Fock space. So any operator on our Fock space, it's a linear combination of products of creation and annihilation operators. So it could be high-weighted products, so it could be a product of a lot of those terms, but still, we can write any operator in terms of such a linear combination. So we can use them to build any operator on the Fock space. And guess what? Also our Hamiltonian, okay? So our Hamiltonian can be seen as an operator on the Fock space. So we can still write our Hamiltonian as a linear combination of products of these guys. And then this is what we're going to see in the next slides.